dataset. So this is how we use Keras's data augmentation API. It's a just-in-time augmented dataset. So what that means though is that it doesn't actually take 1,000 images and make 36,000 images, however how much different augmentations we want. What it does is that during each batch process, it does the manipulation in real time, so that even though it's finished an epoch, the first epoch basically will never be the same as the last epoch, even though it's the same data set, because each image is probably randomly, it's not probably, it is randomly manipulated to generate the manipulations we just saw here. So let's see how we use this. So basically it's quite simple. You'll see it in the code, but this is the essential parts of it here. So we create our image generator here, and we specify the types of augmentations we want. Rescaling is basically the normalizing we did before, where we bring it between 0 and 1. Sharing is basically sort of like twisting the image slightly. I'll show you an example soon. Zoom range is zooming in and out, so we have some of the data that's lost because it's zoomed in and cropped. And we have horizontal flips, and for the test data set, we just simply rescale here, because we don't want to manipulate the test data set. We want the test data set to remain as is. We just want to add the manipulations to the training data set. So this is the second part here. This is the actual generator now. This is where we actually pull the images, and the generator returns the images during training. This was just specifying how we wanted our manipulations to be. So we take what we defined here, which is our train data gen and our test data gen, and we basically tell it to take images from a directory. This is one way you can do it, but I actually find it's the best way. And we specify the folder. This can be the path to the images here. So in our case, it was datasets / cats vs dogs / train. And it automatically finds the classes there. We know it's a binary class because it's 2 classes, but we still have to specify it here. And we basically tell it the target size, which is 150 by 150, which we defined outside of this here, and the batch size. And we do the same for the test data gen here as well. So you can basically read what this flow from directory function does. It takes our image data and creates an iterator, which is a memory efficient method of returning a sequence of data. There's also a flow when we actually have the files differently. So lastly, this is how we actually fit the model now. Instead of actually using the test data and training data and all those things, it's a bit different now when we're doing model fit generator. We specify our train data generator, our train generator I should say. This is where we get our images from, here. Alright. Actually this is named wrong. This should actually be named train data generator, not test data generator. That's my bad. Back to this here, we define the steps per epoch. Now, this is different to what you think. This is the number of training samples here, which would be 1,000 divided by the batch size. Okay, that's our steps per epoch parameter, and it's the same for the validation steps here. Don't overthink this. This is just a particular way our generators actually work, and that's it. We can start training our data set with our data augmentation. Hi, and welcome to chapter 10.4. It's a brief chapter where I talk about the different types of data augmentation that Keras offers. So let's quickly look at it here. So if you go to this link here, you can actually see the number of types of augmentation abilities that Keras has. In practice, the ones I found most useful are just these here. After, we'll go to that link and check out all. But for now, I wanted to explain what sharing was, because a lot of people do ask me what sharing is. Basically, it's a type of distortion where we sort of like manipulate the image perspective that we're looking at it. So imagine this is a square that was here, and after some X sharing, it actually looks slanted like this. That's what sharing does. And fill mode nearest, which I explained in the last slide, basically we can have constant, nearest, reflect, or wrap. That's basically how it looks differently. It's always good to use nearest. However, you can definitely experiment with these again and see. Depending on your data set, if it's like real world images, I would probably always use nearest. However, if it's certain things like numbers or whatever, you may want to try something different, like constant may actually be better for digits and characters. All right? And what's good to know is that nearest doesn't really add new features. It isn't going to confuse the classifier too much. Okay, so what I'm going to do quickly now is go back to our IPython notebook, and I'm going to show you how to create many different manipulations randomly of an image, just for fun. You're not actually going to use this much unless you want to actually see and visualize how your manipulations are taking place. And before we even do that though, let's actually go back to Keras' site, and we can take a look. It's already up here. All of the different augmentation techniques. You have different types of pre-processing and normalization. You have different types of like ZCA and PCA, those type of things that do like feature extraction, and ZCA whitening is quite commonly used, or at least used to be quite commonly used in computer vision. I don't think with deep learning it's used that much anymore, but Keras still offers it, which is nice. We have brightness, we have zooming, channel shifting, different fill modes I mentioned, vertical flips, rescaling, which is what we did before. So it's actually quite useful, and you can actually see some example code here on how to actually use some of these things. Okay, so now let's go back to our IPython notebook, all right? And we're actually going to see, this is, where is it? Here. Let's open it here, and let's actually go to data augmentation here, and let's open up this demo slide here, this demo notebook. So what this does here, it just basically shows you, let's load this data set. That happens the first time you run something with matplotlib sometimes. It doesn't actually show the graph. Alright, so now we see some random digits here. This is with no manipulations right now, an untouched data set. Now, how about we do some random rotations, okay? Oh, I'm not gonna, actually I can run it, doesn't take that long to run. So here we see some random rotations. You can see some of these here in the middle actually don't look rotated at all. The 2 and 7 definitely are rotated. What about random shearing and zooming? Zooming, definitely you can tell this is zoomed, this looks slightly zoomed if I'm not mistaken. Shearing isn't as obvious to see, but definitely I think this 4 is shared slightly, or this 9 is shared slightly. This 4 looks shared, definitely too. But you can see how shearing can take one person's handwritten digit and turn it into maybe someone else's one. So you're creating more data from existing data. What about horizontal and vertical flips? Got no idea what this is, so you actually should not do horizontal or vertical flips on digits. Digits are generally going to always be standardly written unless someone is doing something very weird. I'm not sure why they would do that. So that's fine. We can do some random shifts as well. You can definitely see this 1 and this 5. Actually, all of them have been shifted because they're usually centered in the middle. None of them seem centered right now. And you can apply all at once to get some very random distortions here, which is pretty cool. So you can take a look at my code to see how it's done. And now this is what I wanted to show you. Remember the dog image I mentioned here? Let's bring it up. Let's see how, if we run this combination of images here, and we do this 36 times, what's going to happen. So let's run this. And it saves in a folder called output directory. So let's go to the output directory here. Nice. So now we see we have 36 images. It actually looks like more. Maybe it did not write over my previous images. But now we can see exactly how our image manipulations, what they do to this poor dog. He is flying all over the place, which is quite cool. So you can see how we have one image that has become many, and we can actually play with these parameters here and keep generating more and more types of combinations. So basically this is a nice way to visualize exactly what our image data generator is doing. Hi, and welcome back to chapter 11, where we start taking a look at the confusion matrix, which may sound confusing for now, but it's very helpful, and also viewing our data that gets misclassified by our classifier. It's very important to look at this data sometimes because we need to know exactly what our classifier got wrong and why. So let's look at the contents in this chapter. It's fairly simple. 11.1 basically deals with the confusion matrix, and 11.2 deals with misclassified data and how we can view them. Okay, so let's get started on 11.1. Hi, and welcome back to chapter 11.1, where we go into the confusion matrix and then calculate precision and recall. So let's get started. So before I dive into our IPython notebook and we actually work through an example using scikit's confusion matrix function, let's take a look at what the confusion matrix actually looks like. Now, typically, which I've shown you before, you have basically true positives, true negatives, false positives, and false negatives. And that was in a binary class analysis. Now, I'm going to go a step further and make you understand this concept using a multi-class problem, and we're using actual real-world results for our MNIST dataset. So this big array kind of looks, or this big matrix looks a bit strange. However, you do pick up initially that there's a pattern right here. That is a diagonal where these are very large numbers and then there are small numbers on the outskirts. So what do these numbers actually mean? So let's take a look. Now, I've made it simple. We know we're looking at the MNIST dataset, so we have 10 classes, that's 0 to 9. Likewise here. And what this column here is the predicted value. So these numbers here mean that our classifier predicted a 0, and the true value was actually a 0. So that's why there's a big number here. So predicted a 1, true value was actually 1. So having large numbers in this diagonal is a good thing. Having large numbers outside of this diagonal is a bad thing. So we can see we have some large numbers here. We have an 11, we have a 6, we've got a 5 over here. So now let's take a look at these numbers. So I've highlighted them here. So what do they actually mean? It means that our classifier predicted a 2 when it was actually a 7. So our classifier is confusing 7s with 2s. It's seeing a 7, but it's classifying it as a 2, which is wrong. And likewise for 6s and 0s here, 9s and 4s here, sorry, this one here, and 9s and 8s as well. So what I mean is that, let's look at 9s and 4s. Our classifier predicted a 4, but 5 times it was actually a 9. So we can see the biggest problem our MNIST classifier is facing is confusing 2s and 7s, which is actually a real problem for a lot of humans. My handwriting isn't very good. I'll be the first one to admit that. And lots of times I'm looking at numbers I write and I'm like, is that a 2 or is that a 7? So we can see our classifier is sort of learning generally like how a human would learn, and interpreting or misinterpreting results just like a human, like ourselves, would. So now let's actually work out our recall value based on this real world data. So let's take a look at the number 7, alright? So this is the true classes for number 7 here. So we saw our classifier got it right 1010 times, so that's our true positives here. So how do we get the number of false negatives now? The number of false negatives are basically how many times our classifier predicted a number would have been a number that was supposed to be a 7. So you can see all these times here numbers were supposed to be a 7, but they were actually predicted to be in a different class, like 0, 1, 2 especially. So let's sum this up. This row here, everything here except 1010 will give you 18. And that's exactly what we calculate here, and we get 98.24%, and that's our recall. So now let's move on to precision. So looking at precision, we know it's a number of correct predictions over how many occurrences of that class were in the test data set. That's another way of saying what this is here. True positives over true positives plus our false positives. So again, let's look at number 7, okay? So now we go the other way. This is interesting. So our true positives again were 1010. And what about our false positives? Our false positives here, basically, all this time the classifier was predicting something to be a 7 when it was actually a 0, a 2, a 3, blah, blah, blah. So those are the false positives for 7s. And we just sum this up, everything here. It gives us 1017. There were 1, 2, 3, and then 3 plus 4 is 7, so that's exactly how we get 99.31%. So basically, we don't have to do this manually. Scikit-learn actually generates a report for us automatically that gives us recall, precision, F1, and support. I think you guys know what F1 is. I haven't actually dealt with support, but I'll talk about it now in the next slide. But you can see we have precision, we have recall, and we have our F1 score here. All right. Now, actually, I can talk about support right now. It's actually quite easy. Support is basically, you see the numbers here, 1028. What was that? Go back to it here. 1028 is basically true positives plus false negatives here. So support just gives us that sum here in the column. So if you look at the column 0, let's go back to it. Column 0 would be everything here. Sorry, everything in this row added up here. So this is 977 plus 1 plus 2 plus 3, 980. And that gives us our support here. And support basically is used for how many times our classifier is actually basically missing data, essentially, missing classifications. Because think about it intuitively. We have 980 zeros represented here in this report, all right? Now, what support is telling us here is that we basically had, that's how many zeros were in our report. So now we can actually use that as a basis to kind of gauge what is happening here. So you can also see if there's any class imbalances in this data here. So what class imbalances are essentially, which you can usually check before you even reach this point. You can easily check it when you have your test and training data. Just check to see how many, like the quantities or the sums, or the counts I should say, of data, of each class of data you have in your data set. So how do we analyze our classification report? So basically we can just quickly interpret something here. High recall with low precision. That is bad, and let me tell you why that's bad. This tells us that most of the positive examples are being correctly recognized. That means there are low false negatives, but there are a lot of false positives, and that means a lot of the other classes have been predicted as our class in question. And alternatively, we can have low recall with high precision. What does that mean? It means our classifier is missing a lot of the positive examples, has a high false negative rate, but those that we predict as positive are indeed positive, low false positives. So we can use our classification report to sort of gauge what's actually happening. In this example, everything looks pretty good, all right? But later on, you'll look at some examples where we generate these reports, and you can actually analyze and figure out which class our classifier is having trouble with. So now let's quickly take a look at the code to generate this confusion matrix, all right? And later on, we look at the same code to look at misclassified data. For now, this is the generic MNIST training code you've seen a few times before. It's used in a lot of my examples. There's one thing I wanted to show you here in this file. Basically, when we store history here, some people have asked me, can I save my history file and look at it again? Because I've spent like hours or maybe a week or days training a classifier, and I want to actually save the plots without saving the image. I want to actually save the file. Yes, you can. You can use a Python function called pickle, and basically what it does here, it just stores a file as a pickled file. Pickled file is basically an array of data. It's a method of storage. I'm not going to get into the detail now, but just know it's a way we can store files. So what we do here, we just pickle out, we create a file that we're going to, this is basically us telling us we want to create this pickle file, and then we just pickle dump this file, this the same history.history file we want to save, and done. Close the pickle file and it's done. And similarly, if we want to load this file, we can simply just load it back here, and here we go. Voila, we have our, this is just for one epoch. If it was more than one epoch, it would look a lot bigger, but basically it's a dictionary file or a JSON file for those of you who come from a JavaScript background. And basically, yeah, this is how it looks. We have our loss, accuracy, validation accuracy, and validation loss, and the values for it here. These are the keys and these are the values. So now we can, I did some plots, but these plots obviously for one epoch are pretty much not fun to look at. Just 1 point here, and an accuracy chart, 1 point here, and 1 point here, not that fun. You can actually see it's already quite good there. This is what I wanted to show you. This here is the confusion matrix and classification report. So we import from sklearn metrics both of these functions here. And basically what we do, we just get our predictions here. So we run xtest. Xtest is our test data or validation data through our model.predict classes. And we just print out the classification report. Classification report just takes 2 arguments. We just take the x-test labels here, sorry, the y-test labels here, and the predictions. So basically what we're doing here, we're comparing labels to labels. And the reason we have to use the npmax function is because our labels before were hot1 encoded. So it's not a like for like. We actually have to now reconvert it back into basically a 1-for-1 type matching. So this is basically what our prediction matrix gave us. And basically this is what the classification report looks like, which we saw in our slides. These are the averages here. They don't really tell us that much because they're about the same. Maybe for more interesting data sets and reports, those values would differ. And confusion matrix is done here. Basically the same thing, same exact arguments as above, and we get it here. So that's it for confusion matrix and our misclassification. So welcome to 11.2, where we actually now can find and view our misclassified data. So if you recall correctly, our last classifier was actually confusing 7s with 2s. So how do we actually see the 7s and 2s that it's mixing up? So now let's talk a bit about that. Firstly, this is actually an underused function. I don't see that many computer vision data scientists using this technique to identify the classifier's weakness. I think it's crucial because by looking at what is misclassifying, you can actually figure out, oh, I need more of this type of data to make my classifier smarter, or I need to augment more this way to add some robustness to my classifier. So viewing the misclassified test data can tell us a lot of things sometimes. What is confusing? Are the classes looking similar even to us? Maybe it's a more complex pattern. Maybe we need to add more deep layers. And maybe our training data is mislabeled. That actually happens quite a bit to me, because I tend to label a lot of my data sets myself, which is tedious and exhausting and prone to making errors sometimes. So let's see how we do this now in our IPython notebook. But before I go ahead, let me just show you what this actually tells us. This is some real life data that has been misclassified by our classifier. So it should be data, not date. I'll fix that for you. But basically what happens here is that this is with the data input here, our input number. So it actually was a 6, but our classifier predicted 0. Now this clearly is a 6, so our classifier is doing something very wrong here. This one is an 8, but we can kind of forgive our classifier slightly because it sort of looks like someone wrote a 2 intentionally, and then maybe their pen skipped and then wasn't able to continue with the 8. So possibly because a 2 is the most pronounced or thicker part of this number, I can see why the classifier thought this was a 2. This one was a 9. Clearly, and our predicted was a 9. However, it actually was an 8. So when I said clearly it was a 9, it was an 8. Someone wrote an 8 very poorly and basically made this bottom circle of the 8 very small. Or perhaps it was misclassified data. We don't even know. But let's trust our data for MNIS, and let's assume this was an 8 that was basically misclassified. This one is a 4, when it actually looks like a 9 to me, to be honest. I make my 4s like a 9. I get scolded for that all the time in high school and primary school. So yeah, so we can understand that one. This one, I would say it's definitely a 6 or a G even. I mean, it's supposed to be digits, to be fair. So we can see classifier got this wrong, should have gotten it as a 6 because of basically how it, you don't do a 5 like this. So yeah, so let's go into our IPython notebook and see how we actually create plots or generate images like this. Okay, so how do we find our misclassified data basically from our IPython notebook, from our Python code basically? So let's think about this quickly, all right? We have our test data labels and our test data, and we have our training data, so how do we figure out which labels have been wrong? And that's actually fairly easy. All we need to do is compare y tests with y prediction. And that's what this function np absolute does. All right, it creates an array that stores a value of 1 when a misclassification occurs. And basically we use this array now, this result. We basically create a matrix here that basically when the result is greater than 1, which means that it's basically misclassified, we get the indices here. And these indices now will correspond to the actual digit in y-test in y-train that was actually misclassified. So y-train 247, if you put some brackets here and go 247, that was an actual misclassified data image input. So let's run this, and we get this here. And this does it quite quickly, as you can see. This is providing you actually have ypredict. We got ypredict, basically, if you remember correctly, from this here, model.predict y classes. And then we generated our confusion and classification report. So now let's display it using OpenCV. So I actually commented out some lines here, and that's because if you wanted to load a model that would, let's assume you didn't run this model, and you just wanted to load a model, you can load it in here and classify, and just change the model to classifier here, and basically do that same thing. And I've commented out this line here as well. That was a print statement that was just printing the true labels. Okay, we're going to actually display it in all in one image for the first 10 misclassifications. So let's take a look. Let's ignore this for now. Let's look at this. Exactly. So what it tells us here is that this was the input image 4. This is what it predicted in green, and this is the actual true value of 4. So it's interesting. Let's take a look at another one. This one is actually a 6 and a 0. Then let's keep going. It's an 8, an actual 8, but it predicted a 4. Same for this one, this one, this one. So this is pretty cool. So you can keep going, can go through all the misclassifications if you want to see what is actually confusing your classifier. Hi, so welcome to chapter 12, where we talk about the different types of optimizers, what are learning rates, how do we even manipulate our learning rates during training, and what are callbacks, a very important Keras utility. So these are the 3 sections in this chapter. Firstly, we just go through the types of optimizers and adaptive learning rate methods. We then take a look at Keras callbacks and look at some 3 important callbacks. There are many more, but these are the important ones I would advise you to know. Checkpoint, early stopping, and adjusting learning rates that plateau. And lastly, we're going to use these callbacks and build our fruit classifier. So stay tuned. Okay, so let's start off chapter 12.1 by looking at the types of optimizers we have available in Keras and look at some adaptive learning rate methods. So let's dive in. So optimizers. So what exactly are optimizers? Now you may have remembered in our neural net explanation, optimizers were the algorithm we use to minimize our loss. And some examples of this, which should be familiar to you now, would be gradient descent, stochastic gradient descent, and mini batch descent. So Keras actually comes with a lot more optimizers than those. We have the standard stochastic gradient descent, RMS prop, eta grad, eta delta, Adam, Adam max, and Nadam. So, and a quick aside about learning rates. Now, constant learning rates are generally bad, especially if you start off too big. So imagine after 50 long epochs, when we're thinking we're close to convergence, but then a problem occurs. Our learning rate basically bounces around, and our loss and our training loss and test loss basically stop increasing. That's a bad situation when you're training. So you always want to use a learning rate that's small as possible, without being too small, because a too small of learning rate would just simply take forever to train. So there are so many choices. What's the difference? The main difference in these algorithms is how they manipulate the learning rates to allow for faster convergence and better validation accuracy. Some require, like stochastic gradient descent, setting of some manual parameters, or even adjusting our learning rate schedule, which I'll come to shortly. And then some of them use a heuristic approach to provide adaptive learning rates, which are quite cool. We'll actually see some of the comparisons shortly. So let's talk a bit about stochastic gradient descent and the parameters Keras allows us to control. So by default, Keras uses a constant learning rate in the SGD optimizers, that's stochastic gradient descent. And however, we can set these parameters here called momentum, decay, and also turn off or on something called Nesterov momentum. So let's talk a bit about momentum. Momentum is a technique that accelerates SGD by pushing the gradient steps along the relevant direction, but reducing the jump in oscillations away from relevant directions. So it encourages our gradient descent to head into the direction that is basically reducing the loss. So it doesn't actually go away from that spot, in big jumps at least. Decay. Decay is a setting that decays our learning rate every batch update, not epoch. So be careful how you set your batch size, by the way. This is the only other time batch size becomes relevant in training. A good rule of thumb, though, is for setting the decay is equal to learning rate divided by number of epochs, okay? So that's how we choose our decay value. Nesterov basically is a guy who actually developed a method that solves the problem of oscillating around our minima. Now, oscillating around our minima basically means our learning rates are too big for us to actually converge at the minimum point. And this happens when our momentum is high and unable to slow down. So it first makes a big jump, then a small correction, and after that the gradient is calculated. That's how Nesterov works. So I always encourage you to use Nesterov being true if you actually want to get good convergence or fast convergence too. So this is a good illustration here of Nesterov momentum illustrated. It was taken from this source here, CS231, Stanford's course. So basically, this is actually all the other algorithms combined here. And basically it shows you how momentum actually looks as well. So take a look. It's actually quite interesting. This is SGD with Nesterov enabled, by the way. So you can see it's taking a while to get here, but it will eventually get here. Although the others have gotten there way quicker. Actually, I was wrong in one thing. I just remembered, I'm checking it on my second screen. Actually, no. Momentum actually had Nesterov enabled here. SGD was just plain vanilla SGD. So you can see all of these advanced optimizers got there eventually, except for SGD, which took forever. So let's talk a bit about more of those other algorithms here. Some of these here. Let's start talking about the ones that are available in Keras. So we just saw we set our hyperparameters to control the learning rate schedule. And learning rate schedules are basically either how our learning rates adapt over the training process, be it based on number of epochs that have been completed or other parameters, okay? That's why it's adaptive learning rate methods, and they each work differently. So let's talk quickly about AdaGrad. This performs large updates for more sparse parameters and smaller updates for less sparse parameters. It is, this is actually bad English, it is thus well suited for sparse data. However, because the learning rate is always decreasing monotonically after many epochs, learning slows down to a crawl. So Eta delta actually solves this monotonically decreasing gradient basically in AdaGrad. It occurs in AdaGrad. RMS prop is actually similar to Eta delta, sorry. Couldn't find that much information to explain this, but just remember, these are similar, probably discovered separately, but have similar methods of action. And Adam, which is not really Adam's name, but Adam, it's similar to Eta delta, but stores momentum for learning rates for each parameter, each of the parameters separately. I'll correct these little mistakes here and there before I distribute these slides to you guys. So what does a good learning rate look like? So this is how a loss graph here, and epochs here, this is how it would look if we had a very high learning rate, a large learning rate. Basically, we would never find a convergence zone because we'd be bouncing around everywhere, and our loss would probably just get worse over time. A low learning rate will eventually get there, however, it'll take a while. High learning rate here would eventually get here too, but this actually could be interchangeable, but basically it will get here too. Good learning rates have nice gradual, smooth decreasing steps and basically converge at lower points over time. And finally, if you go to keras.io/optimizers, it brings up a list of all the optimizers and actually how to use with the code here, and what settings that are available to the optimizers. So you can see SGD here basically has some of these parameters here. Nesterov decay, remember I mentioned this to you before. RMS prop, all of these are available here, and some explanations on what they do, what you can tweak is all available on Keras' site. So take a look. Just so you know, in best practice, I find Adam to be one of the best optimizers, and you don't even actually have to go far off from these default values. I would actually just put learning rate to be slightly smaller, but all these values are usually fine. Also, what's quite good to use as well is SGD with a very low learning rate. You can set the momentum and decay according to your parameters I mentioned before, and always use Nesterov as true. Hi, and welcome to chapter 12.2, where we talk about callbacks, checkpoints, early stopping, and adjusting learning rates at a plateau. How we do this automatically in Keras are all made possible by callbacks. So let's take a look and see how it's done. So let's talk about checkpoints first. Now, as you saw in previous training models, when we trained actually the cats vs dogs classifier, we saw we had 25 epochs, but our best results were somewhere at maybe epoch 14 or 15. We got like high 76 or 75%. So what if we wanted to save those weights after each epoch and maybe keep the best model. So after every epoch, what if Keras saved the model and maybe just kept that the best model in memory, so that after every epoch, we keep saving the best and best model. So at the end of it, even like in that cats vs dogs example, at the end, after 25 epochs, the model that we save isn't the last model after the training, 25 epochs, but it would be model number 14, after epoch 14. So this is quite useful in actually just getting, if you want to leave something running overnight and you don't want to actually have to sit down and babysit its training, you can just use this. So let's see how we use this checkpointing inside of Keras. So checkpointing is quite easy. First of all, we just need to import it from Keras callbacks, and basically this is how our checkpoint object is created. So we initialize it here with model checkpoint. We specify a folder for where we want our model to be saved, and we specify what value we want to monitor. So after every epoch, if our loss basically increases, we just use the loss to actually monitor what model is best. We use our mode minimum, so that means we get the minimum loss, obviously. And save best only is true. The reason I said this to true is because why would you want to save models that aren't that good? It just wastes memory and space. And verbose equal 1 gives us a nice feedback when it's actually doing the checkpointing, which we'll see in our IPython notebook quite soon. And basically, we just have a variable here called callbacks. We put this object here into this array. And when we're training, we add this new line here, callbacks equal callbacks. And basically this takes all our callbacks. We just created one here. However, if we wanted to create another type of callback, you just put it in this array as well. And that's it. We look at the lowest value for our loss and save only the best model. So how do we stop training once a model stops getting better? Now, this is another useful feature that can save us valuable computing resources. What if after 20 epochs you stop seeing any improvements? That is, our validation loss or accuracy was no longer increasing or decreasing respectively. So would you want to wait an extra 30 epochs and risk of overfitting and waste all that time too as well? So no, you don't. So even after executing all 50 epochs, checkpointing ensures that we save only the best model, but we're still running a pointless 30 epochs, which is wasteful. So how do we stop this? Now there's a new callback called early stopping. Early stopping basically allows us to monitor a value, and if that value basically stops improving, we stop training. We don't run any more epochs. So this is how early stopping is configured. Similarly for checkpointing, we tell it what to monitor, so we monitor validation loss. We have some parameters here called min delta patience. All right. So what this is here, it's an absolute value, and it's basically the minimum change required before we stop. So basically, basically what size of change we look at, and patience is actually a nice value, nice parameter as well. It tells us how many epochs we wait before we stop. So let's say we're looking at epoch number 20 in my last example, and our validation loss was basically 0.1, and in 21 it was 0.1 again, and in 22 it was 0.1 again. That means we waited 3 epochs, and now this early stopping callback will basically stop training prematurely, which will be a good thing here, because our min delta, which we set at 0, if we set it at a value like say 0.5 or 0.1, basically it would basically look at values at up to 0.1 as being the change. So if nothing improved basically more than 0.1, it will still wait these 3 patience delta epoch cycles here and then stop. So what about this one here? Reducing learning rate on plateau. Now remember I told you we have a number of optimizers before that basically do learning rate adjustments on the fly, using things like momentum and decay and some advanced algorithms and Adam and those sorts of things. But Keras also actually has something that can actually force us to change the learning rate that has been set in those optimizers. So what we can do is basically when it's on a plateau, which means that we can avoid oscillating. Let's explain this quickly. We can avoid having our loss oscillate around a global minimum by reducing the learning rate. And how does Keras even know this? So if no improvement is seen in our monitored metric, typically validation loss, just like early stopping, we just wait a minimum number of epochs, and then we change the learning rate. So, and this is a factor we can change it by, and this is the minimum delta or minimum size we can make our learning rate be, or the change be. Okay, so this is a quite useful feature to use. I actually always use these 3 callbacks in my training. Going forward, we will start using those as well, and it basically saves you a lot of time. You can just leave something, walk away for a couple hours, come back, and you'll see if your training model was good or not. I've seen some people actually do some pretty cool things too, where they hook up basically like texting or notification systems through their Keras callbacks inside of Python, so they get a notification when training has stopped early. That's quite cool. That'll be a fun project for you to do. So that's it for this chapter. We're now going to go into our IPython notebook and train our fruit classifier using some of these methods I've just shown you. Hi, and welcome to 12.3, where we start building our fruit classifier, and we start using some of those callbacks we learned in the previous section. So let's talk a bit about our fruit dataset. It's called Fruit360. Basically, it was part of a Kaggle competition. This is a link to the actual dataset here. It consists of 81 types of fruits, that's 81 classes, and approximately 45 images per class. And all images are 100 by 100 pixels and in color. So these are some examples of our fruits here. Honestly, I can't identify some of these myself. But yeah, we're going to train our classifier to do just that. So let's go to our IPython notebook. Okay, so here we are at chapter 12, building our fruit classifier. So let's bring up this file. But before we begin, I hope you downloaded your Fruit360 dataset. Then I wanted you to put that file, let's go to it here, into this folder. Well, it should have extracted into this folder here. And basically, I want you to make sure that it's named train and validation. It should be, as I've zipped it or compressed it correctly. And you can just take a look at the fruits here. So you can just take a look at some mangoes. I love mangoes. They all look quite similar to each other. Okay, so let's go back to this here. So let's go back to our notebook. And firstly, like we've done in our dogs vs cats CNN, we declare the directories here, and we just create some image data generators for our train and validation, and our train generator and validation generator. Notice it's now categorical, not binary. And also notice we have to declare number of classes here as well. For this dataset, even though the dataset is encoded into 100 by 100 pixels, I'm going to resize it as 32 by 32, basically make our training faster. We use a similar CNN that we used for Safar here as well. And then we declare, this is the important part, let's create our callbacks. So as you can see in the presentation, this one is a checkpoint callback. And checkpointing basically ensures that we save the best model after every epoch. So if we train for 20 epochs and the best model was at epoch 16, that'll be the one we save here. We need to specify a file name. I actually didn't mention that in our slides, but it's not just the directory, it's actually the file name we want to save it as, otherwise it will not work. Early stopping here. Early stopping, the parameters we have set are here, and early stopping basically tells us if this thing has stopped improving, it'll stop. Learning rate and plateau, which wasn't actually used in this example here. However, we could have used it in another example. It rarely happens unless you're training for exhaustive number of epochs, but it's always good to have it just in case. So we create our callbacks here, and I actually did not add it in here. Let's quickly put it in. And basically what we do when we when we fit our model, is that we point our callbacks to our callback array here. So as you can see now, we've trained for 5 epochs here, and basically you can see this output is new. Basically this tells us that a model was saved to here after every epoch. And basically what happened is that after epoch here, it noted that validation loss didn't improve. If we had trained for more epochs, which I probably should have left it for this example, but if we had trained for more epochs, we would have initiated our early stopping metric, and this would have stopped training. So basically, I could have set it to train at 10 epochs, which I probably should have done. Where did I define my epochs? Here, sorry. And you can do it on your own. Set it for 10 epochs and train it, and you'll see it's going to stop after maybe 6 epochs. So let's take a look at our confusion matrix here. It's not printed correctly, and I'll show you how we solve this after. And that's because we have 81 classes in this here. Our classification report, though, is well laid out, but it's a bit tedious to read. You don't get a ton of information unless you actually drill down and see something like, oh, pomegranates are basically bad. Okay? So here's another way to visualize the confusion matrix, which was probably not best visualized at all like that. So here we go. Now, there's a problem here with this. We can actually increase the plot size here. Let's try 20 by 20. It'll probably take about maybe 10 seconds to run. Oh, validation, the generator isn't run. So let's quickly go back here and run this in the beginning. It's good that you actually see these errors and see how I solve it. Okay, that's because our notebook was saved, but it wasn't actually run. And let's run this. This should work now. It's loading our model. That's a model I saved prior to training that one. I think it was a fairly good model, if I'm not mistaken. Ah, there we go. So this 20 by 20 did make a nice difference. And we have a nice legend here as well. So you can see there's a nice diagonal in the middle here. So that is good. Now we can see little spots here and there. This one is here. I'm not even sure what this corresponds to. Let's see. It looks like kumquats, and it's been mixed up with, I think this is mandarins. Not entirely sure, but you can analyze this on your own and take a look and see what's being confused as what. So this is actually a nice visual representation of a confusion matrix here. Okay, so let's test this here. Now I've created this OpenCV thing that actually brings up our fruits and tells us the predicted value and what it actually was. So let's run this. Here we go. So predicted a passion fruit, and actually it was a passion fruit, and that is not how the passion fruits I've seen look, but fair enough. Apparently there's a red banana, and it got it correctly as a red banana. Tomato tree, I think that's type tree. Good. Pear, grape, white or green, looks like a light green to me. Avocado ripe, good to know that it's ripe. Huckleberry, so it's actually getting everything right. This is quite good classifier. And basically we can take a look at our classifier results, which probably should have mentioned before. 83%. But is that the one we actually use? No. The one we actually, with checkpointing, which is very useful, the one we actually used probably was the one that got 92.79%, so almost 93% after just 3 epochs that in each epoch took about just under 5 minutes to run. So this is quite good for training such a complicated data set using our CPU. So let's just run it one more time. Let's see if we should at least get 1 in 10 wrong. So let's try to get 1 wrong. Very good. So yes, pomegranates are a problem. I'll be fair. To be fair, this does look like an apple to me. However, this part of it does not look like an apple. Good. So everything else is correct. So that's it for basically using Keras' callback feature. We've seen checkpoints, early stopping, and learning rate adjustments on plateau. That's it for this chapter. Hi, and welcome to chapter 13, where we're actually going to build some famous CNNs, one called Linet, one called AlexNet and Keras. And then we're going to take a look at batch normalization and see how it improves our results easily. So let's look at the contents in this chapter. We're going to build Linet and then test it on MNIS. Similarly, we're going to build AlexNet and test it on Cefar 10. We're going to learn about batch normalization, and then we're going to use batch normalization in building our clothing and apparel classifier, which is based on the fashion MNIS dataset. Hi, and welcome to chapter 13.1, where we actually start building Linet in Keras. So before we jump into Keras, let's actually talk a bit about Linet. Linet is quite an old CNN. It was actually developed by LeCun, that's how it gets its name, L-E, sorry. And it was developed in 1998, that's over 20 years ago. And it was actually very, very effective though on the MNIS dataset in handwriting digit recognition. And you can visit this website to learn more about Linet. This is basically a sample or an example of how Linet was constructed. This was the input, convolutional layers, the feature maps that generated, another convolutional layer, some more maps, and FC layers here as well. Actually, sorry, this was a max pooling here and max pooling here. So let's look at LayNet here in action. This was this is like a 20-year-old program where we're actually first using an ancient CNN and classifying these digits here. This is quite cool though to see. So now let's jump into Keras and actually start building LayNet. Hi, and welcome to our IPython notebook. We're actually going to build LayNet, so and test it on MNIST. So let's bring this up, and I'm already seeing a small typo right here. This should be MNIST. So basically, we do our usual importing MNIST, transforming our data, blah blah blah, categorical, hot one inputs, all of these things, defining classes, number of pixels, and now this here is LayNet. It doesn't look like much, does it? However, this is the actual model that I just showed you in those slides. Basically, it has two sets of CRP, which is basically convolution, reload, and pooling, done here. Then it has the fully connected layers, and then basically we have our softmax and our usual optimizer. However, we're using Ada Delta and create the model here, only 1.2 million parameters again. And we train it on MNIST, and we save it as an MNIST LayNet model. And these are the results after 10 epochs, and we can see it actually got quite good, 99.31%. That is actually really impressive. And if we go back to our presentation here, this was, let's bring this up as full slide here. This was LayNet's performance here, 93.1 on MNIST. Now that other CNN we used before for MNIST, what did he get? He got very close after 10 epochs as well, 99.15. But you can see 20 years ago, a CNN that was designed, this simple CNN here, actually got such good results. I could imagine 20 years ago, on hardware 20 years ago, how long this would have taken to train though. And nowadays we're using this on a tiny laptop with just dual core CPU, and it trains within maybe half hour. So that's quite impressive. So now let's move on to AlexNet, which is a lot more complicated than LayNet. Okay, hi, welcome to chapter 13.2, where we're actually going to build AlexNet now in Keras. So let's learn a bit about AlexNet. AlexNet was developed by Alex. Was it a coincidence? I don't know. No, it's not. Alex Krivensky, not sure if I'm pronouncing that right. This person here, I'm not even sure if it's a man or woman. Jeffrey Hinton from Toronto, famous guy. Maybe because he was the winner of this competition in 2012. So AlexNet contains 8 layers, with the first 5 being convolutional layers and the last 3 being FC layers. So that's a bit of a different architecture that we have used than we've used before. And it has 60 million parameters. As you can see, LayNet and the CNNs we've used before had roughly just over 1 million parameters. This one has quite a bit, and it has to be trained on 2 GPUs for over a week. And that was in 2012 technology, which wasn't that bad, to be fair. This is the architecture diagram of it here. This was from the actual paper, and I'm not sure why it actually cut out a piece of it here. Maybe it was a mistake they made in LaTeX, for all I know. But this looks kind of strange, doesn't it? 5 convolutional layers here, and then 3 FC layers here. So we can recreate this structure quite easily in Keras, and let's get into it now, okay? This is actually another visualization someone did of this network that it's a bit more easy to visualize here, with the numbers being clearer and the top half of it being visible. Okay, so let's move on to building AlexNet in Keras. Okay, so have it open in this window here. So we're going to test it on Cepha. Now let's see how it goes. So let's load Cepha, the usual stuff we do to load a data set and get our data set in the correct format, hot one encoding. That's good. Now this is the interesting part. Let's replicate our layers here to basically be in the same format as AlexNet as you saw before. So let's get to it here. So we have all of these layers here. We have the 5 conv layers here, and then with number of filters in it appropriately sized. And we have the 3 FC layers here, appropriately sized as well. And let's print out a summary of how this looks, and this is giving us 78 million parameters. Wow, that is quite a bit. And let's see if we can actually start training this on our CPU. Pretty sure it's going to take a while, but let's see what happens. I've actually seen a problem here already, so I'm gonna, actually no, it's fine. I initially thought if I didn't have verbose equal 1 here, it wouldn't actually start and show our training data here. But apparently verbose equal 1 in our model.fit is the default. So that's good to know. So as you can see, let's just take a pause and look at this for a minute or less than a minute. You can see we're slowly going through this. Each batch is taking forever